Okay, so we talk about order statistics. So this problem is basically we have given some numbers, given an array of n element, and the problem is to find the ith smallest element. That is the called order statistics, finding the ith smallest element. We have given n numbers and we need to find the ith smallest element. So this problem is called order statistics problem, or this is called order statistics. Now if I is equal to 1, this is called minimum. So I is equal to 1 means first smallest element, which is basically minimum. I is equal to n, this is called maximum, and for I is equal to n by 2, it is called median, provided n by 2 is n is an even number, otherwise we can put a ceiling or n plus n minus 1 by n plus 1 by 2. Anyway, so if I is so it is basically the median. So now the question is how we can solve this problem in general. So for any I, say for these two problem it is quite simple. So how we can find the minimum or maximum? So we have given an array. So what we can do? We can just scan the array to get the minimum or maximum. So very simple code. So suppose this is a maximum finding, max of A. Okay, so just few line code. So we start with for I. So we are assigning this key value is basically A1, and then we are having a for loop for I starting from 2 to n. We compare with the key, do if key is, so we are finding maximum, do if key is less than ai, then we replace key by the new ai. That is it. And finally, after this loop, we just return the key as a maximum. Okay, very simple code. So we basically need to scan the array. We basically need to scan the array, and every time if the element is greater than that what we have, candidate of the maximum, then we replace that. So this code will take how much time? This is a for loop of size n, this is a linear time, order of n. Okay. Now this is for maximum or minimum. Now suppose we want to find out the second minimum, second smallest element, say I is equal to 2. Then can we extend this code, or say it could be difficult to extend this code even for I is equal to 3 or 4, because we may need to store this and then again compare this. So this simple code will not extend it, I mean for this, for any value of I in general. So I is also part of the input. So basically the order statistics problem is to, we have a array and input is basically a array, input is an array and a I, and output is basically ith smallest element. Okay, ith smallest element. So now what is, so how we can solve this problem in general, like for any I? So the naive approach is we can sort these numbers and then we can go to the ith position and we return that value, that is it. So that is the naive approach. What is the naive approach? So we can just sort this array using any like sorting algorithm. If we restrict ourselves as a, I mean if there is no, if we have to use the comparison based sort, because it is using the, we do not need to use the auxiliary storage for that. Auxiliary storage means that we do not need to bound our input in a some range. Okay, so yeah, so what is the naive approach? So we sort it we sort A and then we return AI after sorting. So, that is our ith smallest element. We sort the elements, we sort the array and then after sorting. So, suppose this is so suppose this is the input 6, 4, 3, 9, 2, 1, 5. Suppose this is the input. This is the array, A array 1, 2, 3, 4, 5, 6, 7. There are 7 numbers. Okay. So, now suppose we want to find out the say 5th smallest element. So, what is our naive approach? We sort this. So, once we sort it, the array will be like this 1, 2, 3, 4, 5, 6, 9. Are you missing any numbers? 1, 2, 3, 4, 5, 6, 9. Okay, fine. So, this is the sorted one. After sorting, so this is 1, 2, 3, 4, 5, 6, 7. So, if we want to find out say 6th smallest element, I is equal to 6, then we just return this one A6 after sorting. So, what is the time complexity? So, this will take linear time, this will take order of n log n, because to make it linear we need to restrict ourselves in a range of the input and also we need to take that size of the storage. Okay. And this is the basically just a return order of 1. So, this will take basically order of n log n, provided we use a sorting algorithm which is n log n. I mean heap sort we can use, even merge sort, but merge sort we need a same size array for the merging. Okay. Now, we want to do something better than n log n. So, that is the algorithm we will discuss today, how we can do better than n log n, because we do not need to sort. I mean sorting is something extra we are doing, because we just ask for the ith smallest element. I also is an input, we do not need to really. So, if we sort, then we can find all the smallest element I for 1 to n. So, that we do not need really, we just need the ith smallest element for a particular I. Okay. So, how to do that? So, let us define rank of an element first. Let us define rank of a element. Okay. Rank of, so we have an array, given an array of some element, n elements, say 6, 9, 10, 2, 5, say 7. We have this element, so this is our input. Now, what is the rank of, say, if I ask rank of say 10, the rank of 5? Rank of a element is basically position of the element in the sorted array. Rank of an element is position of that element in the sorted array. So, if we sort this, so what is the rank of, so if we sort this, then it is basically 2, 5, 7, 2, 5, 6, 7, 9, 10. Okay. So, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. Okay. So, if I ask rank of 5 means basically 2, because position of this 5 in a sorted array is basically it is in second position 2. So, rank of 5 is basically 2, rank of 7 is 4, rank of 9 is 5. So, basically order statistics problem is basically finding ith smallest element, means we are trying to find the element whose rank is I. So, the ith smallest element means means to find an element, this problem is same as to find an element, find the element whose rank is I, the element with rank I, rank equal to I. Okay. So, finding the ith smallest element is same as we are looking for an element whose rank is I. Okay. So, how we can do this other than sorting and going to the ith position and get it. So, that we have to discuss. So, any subroutine you can think for which can help us for this. I mean, we do not need to sort the complete array, but anything, any quick sort any algorithm or any subroutine we use in quick sort that could help us. Yes, partition. So, let us talk about that, how we can use the partition subroutine which we use in quick sort to find the ith smallest element. Okay. So, our partition subroutine in quick sort. So, what we had, what is the partition subroutine basically? Just to recall, suppose we have a array say P to Q. So, what we are doing in partition? So, we choose this AP as a pivot element, first element we choose as a pivot element, and after partition what we are doing? We are dividing the array into two sub array, we are putting the pivot element in this position and all the elements over here is less than x, all the element over here is greater than x. Okay. And this is the position we are returning. We are returning the position of this R if this is P to Q and in the partition. So, this is basically partition call. We are taking the first element as a pivot, our original partition algorithm. We can take any element as a pivot, but for the simple we are taking first element as a pivot and then after partitioning what it is doing? It is dividing the array into two sub array and here it is putting x in such a way such that the left sub array all the element must be less than x and the right sub array all the elements must be greater than x and x is in correct position. So, x is basically p minus x is basically in the rth position. Okay. Now, if we define say r k is equal to r minus p plus 1, okay, then can you tell me what is the meaning of this k? If we just define r minus p plus 1, this is basically our array is starting from p to q. So, this is the position of this is the rank of k, rank of x. So, k is basically rank of x, because if it is sorted in the sorted array x is in right position, x is in correct position. So, what is the position of x? If this is starting from 1, it is starting from p. So, that means r minus p plus 1. Okay, if it is starting from 1, if p is equal to 1, so this is basically rth position, but our array is general array, our index is start from say p to q. So, if p is 1, if our array is starting from 1 to n, p is 1, then this is cancel out, it is r. So, r is basically the rank of the x, because x is in correct position. When you sort it, x position is not changing. In the quick sort, we sort this, x is in correct position. So, that is the divide and conquer we use, but not we are going to sort this. So, what we do now? Now, if we are looking for the kth smallest element, then we got that is our x. Okay. Now, suppose if k is say 7, suppose our pivot element this is 7, rank is 7. So, this is our 7th smallest element. Okay, suppose this is a 7th smallest element, k is 7. Now, suppose we are looking for I is equal to 7, 7th smallest element, then we got I, straight away we stop and happy. Now, suppose we are not that much happy, lucky, suppose we are looking for I is equal to say 4, we are looking for 4th smallest element, we know this is 7th smallest element. So, that means 4th smallest element must be here, because this is the 7th smallest. So, now we call the same function, we look at the same, this is also divide and conquer technique. We look at the 4th smallest element in this sub array, okay, with I is equal to 4. So, this is also divide and conquer technique. We will write the code. Now, suppose we are looking for say 9th smallest element. Now, we know this is the 7th smallest element. So, 9th smallest element cannot be this side, this sub array. So, we need to look at the 9th smallest element here, but we already reached the 7th smallest element. So, we will look at the second 9 minus 7, that is second smallest element in this sub array. So, this is the divide and conquer step. So, we do not need to sort completely, but we will take use of this partition subroutine. So, let us write the code for this. So, this is we called select algorithm. Okay, so this we call select. So, what is the input? A, which is starting from P to Q, and I. Okay. So, so now if P is equal to Q, we return, we stop, we return AP. Otherwise, what we do? We call the partition. We call our partition algorithm P to Q. So, it will choose the first element as a pivot, and then it will just divide the array into two sub array. One is so it will choose, so X is basically AP, and now this is the pth one, and it will return this R. Okay. Now, we take k is equal to R minus P plus 1, and this k is basically rank of X. Okay. Now, if we are looking for kth smallest, I mean if I is equal to k, I is equal to k, then we just return X. Return X, that AP, I mean that pivot element basically, happy, lucky case. I mean otherwise, if I is less than k, then we again call this select on this sub array. So, suppose this is the kth smallest and our I is less than k. So, we have to look at this sub array, we call this is a divide and conquer technique. So, this select is a divide and conquer approach. So, divide and conquer, divide and conquer approach. Okay. So, if I is less than k, then again we call this select on the left sub array P to R minus 1 with this I. Again we call this left sub array with P to R minus 1 and with I. Else if I is greater than k, then again we have to call select in the right sub array R plus 1 to Q with a new I, and that I will be I minus k, because we have already seen the kth smallest. And then suppose if k is equal to say 7, and if we are looking for 9th smallest, that means if this is 7 say, and if we are looking for 9 smallest, that means we have already reached to the 7 smallest here, then we have to look for 9 minus 7, second smallest in this sub array. So, we call this is the conquer step. Okay. So, this is the code. this is the select code, sorry, select, SELECT, select. This is the select code. So, here basically we are using the partition algorithm of quicksort. So, what is the time complexity of this? So, when we will be lucky? We will be lucky if we get this in this sort. In that case, we are calling the partition, it is order of n, that is it, because partition algorithm will take order of n. So, this is a linear time. Now, even if we are not lucky here, so we are calling here, so it will depend on this our pivot element, I mean it will depend on the partition. So, if our partition is say, so if our partition is say half, then we are, so it will depend on the partition or the pivot element. Okay. Now, suppose our partition is say half, suppose x is sitting here n by 2, n by 2. So, if the partition is n by 2 is to n by 2, then what is the recurrence? So, we are having the recurrence T n is equal to T of n by 2 plus theta of n. Okay. So, this is the recurrence for this. Now, this will give us what? This will give us theta of n by again master method. So, this is the lucky case. If the partition is this one. Okay. So, this is the best case. Now, we also have almost best case. Now, suppose partition is not that much good, but suppose the partition is say some little fraction over here 1 by 10 and this is say 9 by 10. Suppose almost best case this one. If the partition is this type of analysis we did in the quicksort. If the partition is this, then also what is the time complexity? Then the time complexity is basically in the worst case, maybe we have to look for the bigger sub array. It is partitioning into 2 sub array, this is the smaller one, this is the bigger one. So, we are looking for the worst case runtime. So, in the worst case we have to go for the bigger part of the array. So, this will be T of n by 10 plus this is the cost for partition subroutine. So, this will again give us linear time by the master method. Not only this, if it is 1 by 100 by 99 by 100. So, if we can ensure that little fraction in one side, then also we are lucky. So, this is the almost best case. We have seen this type of analysis in the, this is the lucky case. But when is the unlucky case? What is the worst case of this algorithm select? So, worst case is basically if we choose our pivot is minimum or maximum, then what is the partition? Then the partition will be 0 is to n minus 1. That is the worst case. We are choosing our pivot minimum or maximum. Then what is the recurrence? Recurrence is T n is basically T n minus 1 plus this is the cost for partition. So, this is again basically theta of n square, which is worse than sorting in n log n and going for the ith smallest element. So, this is the worst case runtime for this select algorithm. Okay. So, now how we can, so but this is the worst case when the partition is 0 is to n minus 1. Now, now how we can ensure that, like we did this type of analysis in quicksort randomized version. Now, how we can ensure that on an average we will be lucky. So, if the partition is sometimes lucky, sometimes unlucky, we have seen also, the idea is to choose the pivot randomly. So, this is the randomized version of this select. So, that is basically rand select. So, what we are doing here? We are basically the same code P is equal to Q, we return a P, and then we are just basically using a randomized version of the quicksort, randomized version of the partition, where we are choosing the pivot element randomly. So, that may give us with a hope that it may we may be lucky sometimes, it may choose the good pivot basically. So, let us talk about this rand partition A comma. So, this is a is starting from P to Q and then I. So, randomized partition A comma P to Q and then the remaining part is same R minus P plus 1, this is the K is the rank of X, and then we just do the same thing. If I is equal to K, then we return K, otherwise if I is less than K, then we have to call again this randomized select, rand select from P to R minus 1 comma I. So, same code, but every time we have to call the randomized version of this. If I is greater than K, then we have to call rand select A to R plus 1 to Q, but now the index is I minus K. Okay, so, this is the randomized version of that. So, in the next class we will analyze this code and we will see the expected runtime of this code is order of n linear time. But in the original version of the select we have seen that in the worst case the partition will be 0 is to n minus 1, in that case it is the order of n square algorithm, but this we will do in the next class the analysis. Thank you.